Welcome to Clear Concepts with Amina Kotwal. Let's see one more example of control systems gate question. This gate question had appeared in 2024 in the ECE paper. The question says in the feedback control system, GS is equal to 6 upon S into S plus 1 into S plus 2. Given is the transfer function block diagram where Rs, Es and Ys are Laplace transfer functions of Rt, Et and Yt respectively. So here Rs is your input, Rt is the input, Rs minus Ys is the Es that goes to the forward path gain given as GS. The feedback path gain here is unity feedback system this is. So the question says if Rt is unit step function, then one of the following is true. The first option says limit t tending to infinity et is 0. Second says limit t tending to infinity et is 1 by 3. Limit t tending to infinity et is 1 by 4. B says that limit et does not exist and et is oscillatory in nature, that is marginally stable. Oscillatory means the system can be called as marginally stable. So let's proceed with the solution of this question. So given GS is 6 upon S into S plus 1 into S plus 1 as given the question. Characteristic equation of any system is given as 1 plus GS HS is equal to 0. Now here GS is given but HS here is 1. HS is equal to 1 because this is a unity feedback system. So putting HS is equal to 1, let's solve this equation. When you solve this equation, you get something like this. S cube plus 3s square plus 2s plus 6 is equal to 0. Now here you have a shortcut to find if the system is marginally stable. If you find the product of the external coefficients of the system, external coefficients, the coefficient of S cube is 1, coefficient of S raised to 0 is 6. So 6 into 1 is 6. This is external coefficient product. Internal coefficient product is the coefficient of S square is 3, coefficient of S is 2. So 3 into 2 is 6. Both these are same. So internal coefficient product is equal to external coefficient product. Whenever this happens, the system is said to be marginally stable. Marginally stable means the system is oscillatory in nature. So for this question, option D is the correct answer, that limit et t tending to infinity does not exist. Et is oscillatory in nature. The remaining options that are given, that leads to a stable system nature, that gives us a hint that the system might be stable, which is not true. Okay, so when limit t tending to infinity et is some constant value or is 0, that means that the given system is stable, which is not true. So this can be explained in detail using Herwitz criteria. This is a shortcut to find out if the system is marginally stable. This can be done using Herwitz criteria. So I'll explain you the Herwitz criteria also. In Herwitz criteria, you need to write down the characteristic equation, writing the highest order of S first and following with the remaining orders ending with S raised to 0. You need to write the highest power of S like this as shown, S cube, S square, S raised to 1, S raised to 0. And you need to write the coefficient. The first coefficient 1 comes here, then 3, then 2, then 6. So 1, 3, 2, 6, 1, 3, 2, 6. For completing the remaining rows, you need to multiply the product of these like this, 3 into 2 minus 6 into 1 divided by 3. So 3 into 2 is 6 minus 6 upon 3, it is 0. So whenever you get an all 0 rows, it means that there is some pole on the imaginary axis. So here itself you come to know that the system is marginally stable, but we still need to find the roots and the remaining roots and come from this. So now at this point, to replace this all 0 row, you need to write an auxiliary equation. How to write the auxiliary equation? Just above this row, the row that is not having all zeros, you take that row and form the equation, take this power, so 3s square, you will have only even powers of s here, so 3s square plus 6 raised to 0, 6s raised to 0. So it becomes 3s square plus 6 is equal to 0 as the auxiliary equation. What you need to do here is you have to differentiate this equation with respect to s. When you differentiate this, if you name this auxiliary equation as a and you do dA by ds, what you get here is 3 into 2s, that is 6s, is equal to 0. Now this coefficient that you get here, you need to write this coefficient in place of 0. So you will make this root table again. You write the remaining coefficients here. Instead of 0, you are going to write 6. So instead of 0, you have replaced this by 6. After replacing this by 6, you need to complete the remaining rows of the root table. So how will you do it? 6 into 6 minus 3 into 0 divided by 6. So 6 into 6 minus 0, that is 6 into 6 divided by 6. The answer is 6. So you write the next coefficient here. You will always see that whenever you do Herwitz criteria and you end up finding the auxiliary equation, you will end up with this, the last element here 6 will match this element here. So you know that you are proceeding in the correct manner. Now to find out these roots, the poles. So what you will do is you will equate this auxiliary equation to 0 and you will find the value of s. So s square is equal to minus 2 you will get. When you find out s, it will be plus minus j root 2. So you have seen that these are the poles on the imaginary axis. So plus j root 2 and minus j root 2 are the poles on the imaginary axis. So these are two roots. The number of roots in the given equation is the highest power of the equation, highest degree here. What is the highest power? 3. So when the highest power of s is 3, it means that this function, this system is having 3 poles, out of which you have already found out the 2 poles. One is plus j root 2, one is minus j root 2. So the 2 poles are plus j root 2 minus j root 2. What remains is 1 pole. So where is that pole? That pole, you have to find out whether it is an LHS or RHS. So when you see below this auxiliary equation, if there is no sign change, it means that the root is in the LHS. Root is on the left hand side. So the third root is on the left hand side. So if the roots are on the right hand side of the plane, it means that the system is unstable. So one root is on the left hand side, which indicates stability. There are 2 roots on the imaginary axis. So combined effect of all these poles, 2 roots meaning 2 poles. Okay, pardon my words. So poles, we have 3 poles, out of which 2 poles are on the imaginary axis, 1 pole is on the LHS. This means that the system is marginally stable or oscillatory in nature. So now if you look back at the question and the options given below, the other options that are given A, B and C, they all say that as time tends to infinity, the value of ET takes a value 0 or 1 by 3 or 1 by 4. So 0 or 1 by 3 or 1 by 4, which indicates that the system is stable in nature. When the system tends to take a definite value at the end of time, it means that the system is stable in nature. Whereas we have clearly seen, using one shortcut method and using Herwitz criteria, that the system is marginally stable as 2 of the poles lie on the imaginary axis and 1 of the poles lie on the LHS. The system is no way stable in nature. So the fourth option of this question, the fourth option is correct. So with this we have solved one control system question of GATE ECE paper 2024. This is the question 13 of the paper. If you want to refer the question paper, you can see it is the question 13 of the paper. So thank you for today. Follow for more such videos. Bye bye.